name is Matt, and I'll be talking about my project for ENME 49 remote sensing at UMD in the spring of 2018 with Dr. Mitchell. Our task for this class was to design and implement a field deployable LiDAR system that runs on a Raspberry Pi using Python and OpenCV to map a specific target on campus. We went out to our target and collected data that consisted of a series of images that we then processed to create 3D points in space to virtually represent the target. By creating a 3D virtual model, we can recreate an entire scene with exact dimensions and locations of objects in an environment which we can then use to better understand things like how the environment changes over time, where objects are located in relation to others, and how objects may interact with one another. During the semester, we talked about the fundamentals of remote sensing, which is the science and technology of attaining information about a target without having a sensor in direct physical contact. There's two main types of remote sensing, passive and active. In passive remote sensing, there's no self-generated radiation used in the sensing process, whereas in active remote sensing, there is self-generated radiation used. In this course, the main form of remote sensing we focused on was active LiDAR sensing. LiDAR stands for light detection and ranging. It uses laser light to measure the time it takes for a packet of photons to make a round trip to a target and back, and uses that to determine the range values for features on the target. We also discussed computer vision this semester. Computer vision involves programming computers to gain high-level understanding of the world around them from digital images and video. Ultimately, the goal of computer vision is to automate tasks that the human visual systems typically do. For this project, we use a geometric LiDAR setup with an active laser element and computer vision to process images taken from a Raspberry Pi to create a virtual representation of our intended target. By projecting a line laser onto our target and recording images, we were able to use OpenCV and Python to generate a series of points and create a 3D point cloud of our target of interest. The target I chose to map this semester is this parking meter located near the Xfinity Center on campus. I chose this target due to its interesting geometry and features. I wanted to see if my LiDAR setup could fully record and display the overall shape and specific smaller features like the rounded edges, tapered sides, slanted top, rounded top in the middle of the crossbar, and the cylindrical base, and how well the 3D point cloud represented those images and to what resolution these features could be displayed. Here's my LiDAR setup for the spring 2018 semester. This LiDAR relies on the geometry of the setup between the laser and the camera in order to get range measurements. There's a two-piece 3D printed mount that's easily attachable to a traditional camera mount. Located here at the bottom of the mount is a red line laser. This laser transmits a continuous series of red laser beams and acts as a transmitter or radiation source for the LiDAR. The red laser then propagates through space until it interacts with an object. The light then scatters off the object and some returns back to the LiDAR itself. This light is then detected by the receiver or Raspberry Pi camera, which is mounted here at the top of the LiDAR mount, which acts as our data acquisition, analysis, and interpretation hardware. The Pi is connected to a laptop through a Cat5 cable right here, and controlled using VNC software. There's also a power cord, which is located right here, which is connected to a mobile power source. Right here, we have an Arduino, which is providing power to our red line laser. On the other side of the LiDAR is an old cell phone. The cell phone has a leveling app that has been calibrated to read 0 degrees when the LiDAR itself is in the vertical position. As the LiDAR is panned up and down, this level app reads different degrees measurements. Coupled with the image of the laser interacting with an object, these degree values allow us to develop a full 3D definition of XYZ coordinates for each of the locations where the laser beam interacts with our object of interest. As we pan the camera, we build a series of 3D coordinates that can then be used to create a 3D point cloud or an overall 3D virtual representation of the object. With the LiDAR set up, the next step was to calibrate the camera with the laser. This figure shows how projecting a laser onto an object into the field of view of the Pi camera allows us to determine the distance to the target. The distance to our target is given by h divided by tan theta, where h of our mount is 12 inches. The angle theta is dependent on the number of pixels from the center of the focal plane, as well as two other values that we needed to calibrate, the radius per pixel pitch and the radian offset. After recording the data from 20 locations at known distances from the wall, and using the setup shown here, we could change these values to match the expected theoretical curve. Here we can see the setup for using the green laser. The laser is 12 inches away from the Raspberry Pi camera. We have OpenCV and Python displayed here on the display screen. We followed the same process for calibrating the line laser. By incrementally moving the line laser back 6 inches and recording images, we were able to verify the distances that the camera recorded to match the values of rho and RPC that we needed to have in order to ensure that our LiDAR sensor was fully calibrated for field testing. Here are the results of fitting the experimental data to the theoretical data for the line laser by adjusting the values of rho and RPC. As we can see, the experimental data matches up well with the theoretical expectations, especially for distances within 5 and 6 feet. With our LiDAR sensor now calibrated, we can go out into the field and begin our mapping. Here we are again on site and actively mapping the parking meter. As you'll see, I start off with the LiDAR at a level 0 degrees and run the Python code on the Raspberry Pi to take the first image. I then tilt the LiDAR mount, run the code again, input the new degree value for the tilt of the setup, and save the next image. I build up a series of these images that are saved into the main folder on the Pi, which can then be easily transferred to my laptop through email. While out mapping, there were a couple of environmental things that I noticed that I was worried may impact the quality of the data that I was taking with my LiDAR. For instance, in this image, there are clearly many streetlights in the parking lot that created a significant amount of noise in the image. In addition, surprisingly, the brake lights of the cars behind the parking meter were being picked up in the Python code and plotted as points in the point cloud. Here, we can again see a very bright and prominent streetlight behind the front of the parking meter. Also note, there's a car coming towards the camera in the left half of the screen. This intersection was an unexpectedly busy one at night, and so I often had to wait to take an image until a car passed and the parking meter wasn't being illuminated by the car's headlights. And another image of the large amounts of noise in the background of the parking meter. In the background is the Xfinity Center, which is lit up 24/7. Additionally, the blue Honda parked here gave off a noticeable glare even after its paint has been exposed to nearly 15 years of weather and sunlight. Ultimately, I decided a good plan of attack was to use an old board that was lying around my house as a physical filter to block out as much of the ambient background noise as possible when performing my mapping. In addition, as we will see, some of the noise was still picked up in the data, but using some code in MATLAB, we can relatively easily remove a lot of the unwanted data in order to get a detailed picture of the intended target. We can see in this picture that the streetlight from before is blocked. So now that we've adjusted for some of the noise, let's go take a look at the data that we recovered. We successfully transferred our photo images from the Raspberry Pi over to our laptop through Gmail. Here you can see we have all 40 images that we took when we went out and mapped the parking meter, and now we can use those to transfer over to the code here. So here's the code we're using to create the 3D point cloud of the parking meter. As we scroll down, we can see that we have our row and RPC values that we derived from calibrating the sensor. When we go a little bit further down, we can see that we're writing it here as the front new, and then we'll create the text file that we'll use to upload the 3D point cloud into MATLAB to get a more effective description of what this thing looks like. So we'll go ahead and run the code and let Python go ahead and start combing through our images so we can calculate the values that we want. So now Python's running through the images. As it scans through one at a time, it picks out the points in the image that represent the red lines and then gives the coordinates X, Y, Z values. So that way we can create our 3D point cloud in MATLAB. All right, so we've taken all our data from Python and we now have it in MATLAB. We're going to go ahead and take the front new data text file that we created and assign it to X, Y, Z variables. So X is the first, Y is the second, and Z is the third. Then we'll go ahead and plot it as a point cloud. So here's our image of the point cloud here. We can clearly see the front of the parking meter, some of the features like the tapered edges, the rounded sides, the sign, and the circular shaft coming up. Next, we're going to go ahead and take those values for all 4 sides and import them into different matrices, and then assign different variables X, Y, Z for all 4, so X4, Z4, Y4, and so on and so forth. Then we'll plot all 4 point clouds on top of each other, and so here we have it. We can see all 4 point clouds now there, kind of overlapping each other. We have the right, the left, the front, and the rear now. So next we're going to do is translate these things around. So now we can assign the different variables for different parts in the matrices, like X, Y2 is the first column, X2 is the second column. Same thing for the X3 and Y3, switching them around to basically flip our images around. So we'll do the same thing, we'll go through and plot them with PC Show. All right, so now we can see we've clearly rearranged our point cloud images and they're in the right orientation. Our next step now is to go ahead and rotate some of these around, so the left and the right here to flip it over, and the same thing for the front and the back to flip it over. So we'll do that. We can go ahead and just change the signs on the X2 to negative and the same thing for the Y4 to negative, and that'll flip it over. So when we plot the point cloud, we'll see what it looks like. So now here it is, completely flipped over. So we can see here's the left side, the right side, the front, and the back, all ready to go. Now we just need to translate these guys together so that way we can have a full image of the parking meter. All right, so now we've done some translations here. So we moved things about 44, 42. A good note is that when we were doing this, they were about 45 inches apart when we were taking the data. So these numbers correspond to what we would imagine or should expect them to be overall. A couple translations in the Z direction as well, just to match the height. All right, so here is the point cloud now stacked on top of each other. We can clearly see the parking meter on all four sides filled in now. We have a little bit of noise and some of those features that we talked about from before. Just looking at it, you can see like the table in the background, the table's legs in the background as well for the noise. So our next step will be able to take some of that noisy data and filter it out in MATLAB. But overall, it's a really good looking point cloud. All right, so in order to filter out the noisy data, we're going to use this for loop here. Basically what it does is it'll run through every single one of our values in our text file and make sure that they fit within a certain range of X, Y, Z values to get rid of all the noise that's outside. We actually do this for all four different text files to ensure that all four are filtered, and then we'll go through and assign them final values and then plot them in a point cloud to basically clean up our final data. All right, so here's the point cloud cleaned up without any of that noise that was outside before. It looks exactly like what we'd expect it to look like for our parking meter. Again, some of those key features are still there as well. So our next step now is to take that point cloud data and make it into a mesh file. So what we did, we took those points, we put them into a matrix, X, Y, Z for all four of them, and then we took that and transposed that matrix to make sure it was in the correct format. And next we write a text file with that data, and then we'll take that text file and print it out using the fprintf command in MATLAB itself, and then we'll have it ready to go on our desktop that we can use to create a MeshLab file. So here's MeshLab. First thing we're going to do is open up the text file that we created. So here it is here. We'll open it, change it, and here's our point cloud. So here's a parking meter. We'll change the point size to get a better picture of what it looks like. Looks good. Okay, next step. It's going to show the normal vectors, so that way we can make sure we know exactly what direction normal vectors are pointing for meshing. Then we'll go through and compute the normal vectors. So if we do that, we can see they're kind of all pointing in different directions. Ultimately, we want them all to be pointing in the same direction, so we'll need to change some of these numbers to ensure that the meshing comes out complete and well-defined. So we'll change this up about 30. We can see it changed it a little bit, but ultimately, we still want these vectors to be pointing in the same direction. So after some playing around, I got some of these relative numbers, so we'll put this at 9,000, flip things, and use trackball center to create the final mesh lab here. And you'll see, perfect. Our normals are pointing all in the same direction. They're all pointing inside. So when we mesh the final file, it should look really good. So our next step here is now to actually go through and make the mesh. So we got the values here. I'm not going to change any of these numbers. I'll hit apply. And just waiting for the mesh to generate. And there it is right there. It's a pretty good mesh. There's a little bit of a cover on the middle there. But it looks just like the parking meter there. Rounded edges, the tapered sides. We got the sign and the cylindrical component in the middle there as well. So next we'll go ahead and eliminate some of this part in the middle using the MeshLab software here, so we can create this gap here. And we'll go through and continue to do that just to make sure that the middle piece is open, and then it looks a little bit more like our parking meter in terms of like the middle part there. Again, just looking at some of the key features in this, it ended up turning out really, really well. All right, so we cleaned up our mesh file here, got the space in between the two parking meters cleared. And so we can take this now that we have a 3D mesh, and import it into Creo. So the first thing you have to do is you have to export the mesh as, change it to an STL file format. So that is right here. And then we'll save it as a new mesh. So I've already saved it here. And then we'll go over into Creo. I'm going to actually open it. So we've opened the mesh file in Creo as an STL file, and we can see here's our parking meter. So one thing to note for any 3D prints, there is a little bit of space here, so I have to make sure that gets filled in. We can see roughly some of the features that we had mentioned before. Obviously, you can clearly make out that it's a parking meter. We have the sign here in the front. The shaft here, or the cylindrical base, kind of got pieced together. Looks a little bit like a rib cage. We can see the rounded shape here, though. And up here, obviously, very clearly, the rounded protrusions on either side of the parking meter itself. So it does a pretty good job of matching what our parking meter looks like. It kind of looks like it snowed a little bit on it, but that's okay. It's actually pretty cool. Maybe we can do something interesting with that once we 3D print it. So there we have it. That's my project for ENME 49Y remote sensing. It's the parking meter. Overall, the class taught me a lot about remote sensing. I didn't know much about LiDAR coming into it, and being able to actually build and test a full LiDAR mount system, a geometric one, was actually really cool. And being able to 3D print the final part was also really awesome. So again, learned a lot about this class. Special thanks to Dr. Mitchell, all my classmates, and UMD for giving us the opportunity to do this.